Hello, my name is Gavrila. For the past 4 years, I've been heading the Intelligent Vehicles group at TU Delft in the Netherlands. Before that, I worked nearly 20 years at Daimler R&D in Germany on environment perception and driver assistance. In this talk, I would like to give an overview of our recent work on 3D semantic scene analysis in urban traffic. I will cover work that recovers various 3D environment representations, bounding boxes, Stixels, and implicit functions from various sensor data, vision, LiDAR. I will start by discussing the new 2.5D Eurocity person dataset that we introduced at the Intelligent Vehicles 2020 conference and mention some of the experimental work that uses it. Work on person depth estimation for monocular vision and 3D person detection using LiDAR and monocular vision. Both works are presented at this conference, and I refer you to those individual presentations for more details. This video shows the output of a state-of-the-art 2D object detection method, FASTER RCNN. Detected pedestrians are shown in green and riders are shown in red. Results are quite remarkable considering that these are single-frame results before any tracking. Even persons which are partially occluded are well detected. This video showed what is possible when training state-of-the-art object detection methods on a large dataset. In this case, we used the Eurocity person dataset, which we recorded in collaboration with Daimler. It involves nearly 250,000 of distinct persons annotated, coverage from 31 cities across 12 European countries, diverse weather, 4 seasons, day and night, and last but not least, accurate manual annotations. By its size, diversity, and annotation accuracy, Eurocity Persons brings person detection benchmarking to a new level. We implemented an evaluation server so that authors can submit their result and see how they compare with the state-of-the-art by means of a leaderboard. The original 2D ECP dataset was introduced last year. What we wanted to do now is to enrich the dataset with depth information for the 2D image annotations. We had LiDAR data to our disposal, but we wanted to avoid starting from scratch and annotating 3D bounding boxes in this LiDAR data. Instead, we developed a method to automatically attach depth information to the existing 2D bounding box annotations using LiDAR data. We use the term 2.5D to indicate that the resulting object annotations are assigned a single depth level rather than being annotated as 3D bounding boxes. This uplifting principle from 2D to 2.5D is straightforward once vision and LiDAR sensors are externally calibrated. In practice, one still needs to deal afterwards with some pesky issues related to time synchronization, ego motion compensation, and depth segmentation, coping with partial occlusions and background objects. I refer you to the below reference for the details. This video illustrates the before-mentioned uplifting procedure. The upper right window shows the annotated 2D bounding boxes, and in the lower window, the 3D LiDAR points that are associated with them, color-coded. As you see, the outcome is quite satisfying, the partial occlusions in the image annotations notwithstanding. And once we have the 3D points of an object, it is relatively straightforward to determine its overall depth, and it is possible to place a 3D bounding box around it once one assumes some typical person extents. Here you see an overview of 3D person datasets. The last column of the table relates to the new 2.5D ECP dataset. Compared to the frequently used Kitty dataset, one sees that the new ECP dataset is 1 order of magnitude larger in terms of the number of pedestrians and riders. Its headline count for pedestrian and riders is less than that of other recent large datasets, but this needs to be put in context because the other datasets list annotations obtained from successive frames which frequently involve the same physical person, whereas ECP annotations are 4 seconds apart and are likely to involve different persons, thus increasing diversity. Diversity in geographical sense is another strong point of the ECP dataset, as it is recorded in 30 cities over 12 European countries. Finally, no blurring of faces is performed, thus avoiding the introduction of a possible bias in image-based detection methods. To visualize the KITTI and the ECP 2.5D datasets, we plotted the position of each person annotation with respect to the ego vehicle in bird's eye view. The vehicle is positioned at the origin. Each pixel in these plots indicates an area of 1 square meter, and the color indicates the number of person annotations in that area following the legend on the right. Comparing the two datasets, for example, for the pedestrian case, we see that the ECP dataset is much larger in size. We can also see that there is a comparatively large number of objects at larger depths in the ECP dataset, making it more challenging for object detection. One can also observe some other nice details in these plots. For example, in the ECP plot for pedestrians, there is a band of lower density running from the bottom to the top of the plot, right in the front of the vehicle at 0 lateral distance. This is to be expected, as pedestrians will be less likely to walk within the vehicle path. Another nice detail is the higher pedestrian density on the right of the vehicle, which of course is the outcome of right side traffic on European roads, with pedestrians on the right, pavements closer by and less occluded. Now we have the new ECP 2.5D dataset, we can evaluate a proposed monocular depth estimation method for persons. We add an additional output head for depth estimation to the standard YOLO version 3 2D person detector, which has output head classification and bounding box regression. See diagram. In fact, depth estimation regresses to two values, mean and standard deviation of a normal distribution. Doing so allows us to obtain a sense of uncertainty in the depth estimation. For training, we're using the log likelihood loss for depth. Let's see some qualitative results of monocular depth estimation for persons. On top, we see detected 2D persons with a YOLO detector, the LiDAR points that were associated with the 2D person ground truth annotations by means of the uplifting procedure I described earlier are also shown in various colors. Estimated depth is indicated by the blue ellipsoids. Uncertainty regions are also shown by bluish elliptical regions on the ground plane, encoding mean and standard deviation of depth estimation. We see that the ground truth person locations and their monocular estimates are quite close to each other. This even holds for this partially occluded child in the image on the top upper right. If we look at the ground truth and estimated location highlighted now in red in the lower image, they are pretty close by. Here are some other qualitative results. Ground truth and estimated depth are overall close by, but we also see a real tough case of this person in the image upper right in the red being strongly occluded, and in the 3D view in the bottom image, we see that the depth estimation of this occluded person is quite off, but at least we see that the uncertainty region is large. I refer you to the paper referenced earlier for quantitative results. Whereas previous slides dealt with person 2.5D localization for monocular video, we now discuss the outcome of an experimental study on 3D person localization, meaning estimation of full 3D bounding box, center location, and box extents. We are comparing two methods, point pillars, which uses LiDAR data, and AVOT, which uses both LiDAR and monocular vision data. Further, we are looking at two datasets, the KITTI and the ECP dataset. This is a busy table, so let me guide you through it. The table rows relate to which methods were used and on what training sets, and whether LiDAR intensity was used in addition to 3D point cloud data. The table columns relate to what test set was used. One observes following results from the table. First, as shown in bold, the best performing network for each dataset is point pillars with LiDAR intensity trained on the corresponding dataset. This shows that there is relevant information in the LiDAR intensity. Second, performance on ECP 2.5D is consistently lower than on KITTI for both point pillars and AVOD, following earlier statements that this dataset is more difficult than KITTI. Third, the best cross-dataset performance is found for point pillars trained without intensity. So while there is relevant information present in the intensity, it presently does not carry over to the other dataset. One should say that cross-domain adaptation for these two datasets is rather weak. Here we show some typical detection results on the ECP 2.5D dataset using point pillars. The image shown is for reference only and is not used by point pillars, as it uses only LiDAR data shown below. Point pillars does a pretty good job in correctly detecting people. See the yellow boxes, but it also makes some mistakes. So the false positives are shown in red, and they include the back of a scooter and a traffic pole, and the one false negative in this frame is shown in purple. Due to the low number of LiDAR points on this pedestrian, it is not detected. So far, I talked about bounding box representations obtained from monocular vision and/or LiDAR data. Now let's move on to the derivation of a Stixel representation from stereo vision. The term Stixels is derived from sticks and pixels. Stixels are stick-like superpixels in a disparity image which represent bar-like structures, either sticking out vertically from the ground plane or lying on the ground plane. As such, they can represent obstacles, sky, or the ground plane. Stixels can represent the environment quite efficiently, while at the same time being quite expressive in representing details of the scene. For example, we are able to represent about 1.4 million pixels in image on the left by only 3,000 Stixels in image on the right. This gives a good compression factor. And also the details of the car on the left, for example, are captured quite well. On the left, we see an image of a van. If we consider the depth profile along the vertical blue line, we see in the adjacent plot how Stixels would represent it, by one Stixel on the ground plane, shown in green, and two Stixels to represent the van and the sky above it. Moving one plot further to the right, we see what the real disparity measurements from stereo vision would look like. On the right, we see a second example of an original image Stixel representation of the depth profile and actual measured depth profile. Schneider and others added object class label to the geometric Stixel representation and called the outcome semantic Stixels. Still, open problems with this representation remained that a single Stixel may overlap two objects of the same semantic class, and Stixels of a single object are not connected. But what we are interested in are object instances and their class label. In work published at the Intelligent Vehicles Symposium 2019, we integrated object instance information in the semantic Stixel computation. The benefits are a richer environment representation, we call it instance Stixels, and more accurate results than by a late fusion of Stixels and instances. So Stixel computation involves an energy minimization over all possible Stixel combinations within a Stixel column. There is a pairwise term relating how likely combinations of ground, obstacle, and sky Stixels are. There are unary terms, which minimize the disparity changes or the amount of different class labels associated with pixels within a single Stixel. And we added a unary term which minimizes the spread in image location of the object centers estimates for each pixel within a Stixel. The processing pipeline for instance Stixels is as follows. We train a convolutional neural network, a CNN, that provides for each pixel an offset to the object center. We furthermore have a CNN that provides class probabilities. Finally, we have disparity information coming from the stereo vision. And these three sources of information are combined in the energy minimization process of the Stixel computation. The output channels are object instance, class label, and depth information. Thus, the scene represented in the left lower image is segmented into the object instances in the right lower image, and each Stixels adheres to the object boundaries. Let's examine quantitatively how the performance versus efficiency trade-off is for instance Stixels versus the baselines. In this plot, the vertical axis denotes the average precision of instance segmentation. Higher is better, and the horizontal axis denotes processing speed. To the right is better. So let's consider the instance Stixels, abbreviated by IS and by small triangles, as proposed, versus the baseline where first semantic Stixels are computed and then instance segmentation is done as a post-processing step based on these Stixels. And this is denoted by SS plus I and a small rectangles. There are two variants of network architectures considered, shown in green and blue. What we can see is that for the green and blue entries, the instance Stixels, the IS, outperform their baseline and have a better average precision performance at the same processing speed. We also have a second baseline that combines semantic Stixels with a post-processing step for pixel-based instance segmentation with the UPSNet network. So this baseline is quite slower while not improving the instance average precision performance. See the symbols on the left in the plot. Let's see some qualitative results. The colors denote the various semantic classes, white borders denote the object instances. This fly-through gives you an impression of the quality of the recovered spatial 3D environment. And now we are back to the 2D view. These are quite challenging scenes with a lot of objects, cars, pedestrians, and we'll see another snapshot where we move to the 3D fly-through to observe the recovery of the spatial environment. So far, I've talked about bounding box and Stixel representations for the environment. The last part of the talk covers work shown at the Intelligent Vehicles Conference 2020 on functional and a continuous 3D scene representation using LiDAR data. We propose a network for spatially conditioned scene segmentation, shortly SCSSnet. It is able to represent the 3D geometry of large outdoor scenes. It generates semantic predictions for all objects in a scene, and does so using a single 360-degree LiDAR scan as input. Rather than representing the 3D environment explicitly by a discrete voxel grid with semantic information attached to it, we represent the environment implicitly by a continuous function. This scene segmentation function takes as input a 3D scene location and provides as output a probability vector of dimension n+1, namely the probability that this location is one of the n semantic classes plus the free space class. And by assigning each point in space to the class of maximum likelihood, we obtain a semantic class. By observing where the decision border is between one of the semantic classes and a free space, we obtain object surfaces. We can evaluate the scene segmentation function at arbitrary many points, thus being able to capture fine geometric details without the discretization artifacts of a voxel grid. But how do we obtain this semantic segmentation function? Certainly, besides a query 3-coordinate, the function also needs to take the sensor measurements into account. We implement this semantic segmentation function by an encoder-decoder architecture. The encoder captures the sensor measurements and transforms them into a latent state vector. This latent state vector is combined with a query 3D coordinates in a decoder to output the class probability vector. For details on the encoder and decoder architecture, see the actual paper. To improve the performance of the encoder, we limit its spatial support. Thus, we employ a grid over the ground plane of the scene, and the encoder only covers the area of a grid cell. To capture details at multiple resolutions, we employ 3 grids of various spatial resolutions. Thus, the encoder provides spatial context at multiple resolutions, in our case at 3 resolutions, as depicted in a figure. To classify a query point, neighboring latent vectors are used, and the class predictions are weighted by a bilinear interpolation scheme. We train our method on the LiDAR point clouds of the Kitty odometry dataset. These have been recorded with a Velodyne sensor with 64 scan lines. All LiDAR points have been annotated with a rich set of 19 semantic classes by the Semantic Kitty dataset. The Semantic Kitty dataset also features a semantic segmentation benchmark on LiDAR data, where we submitted our test set results for evaluation. This benchmark is based on the popular mean intersection over union metric. The baseline results, shown in the top 3 rows, are all based on the projection of the LiDAR points on a cylindrical image plane. The bottom row shows the performance of our proposed method. Even though our method is designed for the semantic prediction of the complete 3D scene and to differentiate between occupied and free space, it still outperforms the image-based methods for nearly all semantic classes, as indicated by the bold-face numbers. Let's take a look at some qualitative results. The left image shows the point cloud given as an input. The middle image shows the resulting scene segmentation with our proposed method. And the rightmost image focuses on the ground plane segmentation. I've reached the end of my presentation, so let me summarize. I've given an overview of our recent works, which cover various semantic scene representations from various sensor types. These works are categorized in this table. The jury is still out on which representation is most appropriate for what applications and for what sensors. Grid-based representations like occupancy grids or voxels are often used in intelligent vehicles and robotics applications to represent a static environment. Object-centered representations like bounding boxes are typically used to represent dynamic objects like road users. This dual representation requires additional bookkeeping when previously static objects start moving, or conversely, when dynamic objects become static. Instant Stixels seem to be an interesting middle ground as a representation between, on the one hand, point clouds and voxels, and 3D object bounding boxes on the other. Still, Stixels are quite strongly linked to disparity maps and to the stereo camera sensor. Beyond Stixels, the 3D functional representation for the environment seems quite appealing, especially in the deep learning era, as it can be learned end-to-end and is continuous. It will be interesting to develop it further. Main themes going forward are how to do sensor data fusion and temporal integration using the above representations. Thank you for your attention, and thanks to my PhD students and colleagues that performed the actual work that I presented.